Section: Introduction. In this section, we will discuss autoregressive models, which are commonly used in natural language processing to predict the next word in a sequence based on previous words. These models work well with discrete data, like language, where inputs and outputs are categorical. However, there has been a focus on adapting autoregressive models for continuous data, such as images, by converting them into discrete representations using techniques like vector quantization. We aim to explore whether autoregressive models must always be paired with vector quantized representations. The key idea is that the autoregressive nature of these models, predicting the next token based on previous ones, does not depend on whether the data is discrete or continuous. What matters is modeling the probability distribution for each token, which can be done using a loss function to generate samples. Instead of relying on discrete tokenizers, we propose a method that uses a diffusion process on continuous data to model the per-token probability distribution. This approach involves predicting a vector for each token, which is then used in a denoising network to represent the output distribution. By training this network alongside the autoregressive model, we can eliminate the need for discrete tokenizers and benefit from higher quality continuous tokenizers. We also introduce a generalized autoregressive framework that combines standard autoregressive models with masked generative models. This framework allows for predicting multiple tokens simultaneously in a random order while maintaining the autoregressive nature. By using our diffusion loss, we show improved generation quality across various models without the need for vector quantization. Our method proves effective, fast, and flexible, showcasing the potential for advancing autoregressive image generation and extending to other domains in future research. Section Summary. In this section, we explore the necessity of coupling autoregressive models with vector quantized representations. We propose a novel approach that leverages diffusion procedures on continuous valued domains to model per-token probability distributions, eliminating the need for discrete valued tokenizers. Our method, called diffusion loss, enhances autoregressive image generation by improving generation quality, speed, and flexibility without relying on vector quantization. Section: Rethinking discrete valued tokens. In this section, we revisit the roles of discrete valued tokens in autoregressive generation models. We denote the ground truth token to be predicted as x, which can be represented as an integer between 0 and k with a vocabulary size of k. The autoregressive model generates a continuous valued vector z in d dimensions, which is then processed by a classifier matrix to predict x. This process creates a categorical probability distribution using a softmax function. To ensure effective generative modeling, two key components are needed: a loss function to measure the difference between estimated and true distributions, and a sampler to draw samples from the distribution during inference. These components are crucial for modeling the distribution accurately. When it comes to modeling arbitrary distributions, denoising diffusion models provide an effective framework. In our case, we aim to model the distribution for each token rather than all tokens jointly. The goal is to predict the next token x based on the vector z generated by the autoregressive model. The loss function and sampler can be defined following the principles of diffusion models. At inference time, sampling from the distribution p, x, z is achieved through a reverse diffusion procedure. This procedure involves a series of steps to generate a sample x_0 from the conditional distribution. By incorporating a temperature parameter, the diversity of samples can be controlled, similar to how it is done in autoregressive models using categorical distributions. In the context of image generation, autoregressive models predict the next token in a sequence based on previous tokens. This prediction process involves generating a conditioning vector z(i) using a network and then modeling the probability of the next token given this vector. The diffusion loss can be applied to improve the modeling of this conditional probability, with gradients backpropagated to update the network parameters for better predictions. Section Summary. In this section, we revisit the roles of discrete valued tokens in autoregressive generation models, where X represents the ground truth token to be predicted next. The autoregressive model generates a continuous valued vector Z that is then projected by a classifier matrix W to model a categorical probability distribution. We explore the concept that discrete valued tokens are not essential for autoregressive models, emphasizing the importance of modeling a distribution with defined loss functions and samplers. Section: Unifying autoregressive and masked generative models. In this section, we demonstrate how masked generative models like masked autoregressive (MAR) models can be seen as a form of autoregression, specifically next token prediction. In masked generative modeling, the models predict a random subset of tokens based on known or predicted tokens by permuting the token sequence randomly and predicting multiple tokens based on previous ones. This process can be viewed as estimating the conditional distribution of a set of tokens to be predicted at each step. We refer to this variant as masked autoregressive (MAR) models, which can predict multiple tokens simultaneously in a random order. Our implementation includes a denoising MLP with a few residual blocks for denoising, conditioned on a vector produced by the autoregressive or masked autoregressive model. We use bidirectional attention to predict unknown tokens given known tokens, randomly sampling a masking ratio during training. At inference, MAR predicts the next set of tokens by gradually reducing the masking ratio with a cosine schedule and applying temperature sampling with fully randomized orders. In our experiments on ImageNet, we evaluate the performance using FID, IS, precision, and recall metrics. We find that even a small denoising MLP can yield competitive results, and increasing the MLP width improves generation quality. The diffusion process follows a 1,000-step noise schedule during training but fewer steps during inference, with 100 diffusion steps being sufficient for strong generation quality. The temperature in the diffusion sampler controls diversity and fidelity, impacting the quality of generated samples. Section Summary. In this section, we demonstrate that masked generative models like MaskGIT and MAGE can be unified under the broader concept of autoregression, specifically next token prediction. We introduce masked autoregressive (MAR) models, which predict multiple tokens simultaneously in a random order, akin to next set of tokens prediction. MAR differs from MAGE by sampling tokens with a temperature applied on the probability distribution of each token, ensuring a fully randomized order for both training and inference. Section: Diff loss. In this section, we examine the speed-accuracy trade-off of our multiple autoregressive regressor (MAR) model compared to its autoregressive (AR) counterpart and the diffusion transformer (DIT). MAR has the advantage of predicting multiple tokens simultaneously by adjusting the number of autoregressive steps during inference. Our MAR model demonstrates a superior trade-off compared to AR, even when AR utilizes an efficient KV cache. Additionally, when incorporating diffusion loss, MAR exhibits a more favorable trade-off than DIT, a popular model that captures token interdependence through a diffusion process across all tokens. Unlike DIT, which involves the entire transformer architecture in its diffusion process, our method achieves better accuracy and speed by employing a smaller MLP for diffusion. Remarkably, our model can generate results in less than 0.3 seconds per image with a strong FID score below 2.0. We conducted benchmarking against existing systems, varying model sizes and training for 800 epochs. Similar to autoregressive language models, we observe promising scaling behavior in our models. Our models achieve a FID score of 2.35 without CFG, surpassing other token-based methods significantly. The top-performing model in our evaluation attains a FID score of 1.55. Showcasing competitive performance against state-of-the-art systems. Qualitative results are visualized in the accompanying figure.